Hey APC kids, Campbell here. In this video, we're going to talk about static equilibrium. Now, if you remember static equilibrium from AP Physics 1, it's when a system isn't moving linearly or rotationally. And so our two conditions for static equilibrium are the sum of the forces equals 0, both in the x and y directions, and the net external torque is 0. So we're also in rotational equilibrium. Now, we've talked about forces in our previous units, but what about torque? Do you remember what torque is? Torque, which is symbolized by a tau, is the force that causes something to rotate about an axis. And so if I have a net torque, I'll have angular acceleration. But if the sum of the torques equals 0, then I'll be in static equilibrium. Now, remember that torque, there are three factors that determine the magnitude of the torque. And if you had me for AP1, I talked about how I was a great door slammer when I was a kid. And so I knew the three things that actually, increased the magnitude of slamming my door. So those three things were how hard I pushed the door, so the magnitude of the force, where I pushed the door, where I applied that force, and the angle at which the force is applied. So if I apply the force at the end, great torque. If I apply the force in the middle, not so much. And if I apply the force, at an angle that is along the thing I'm trying to rotate, nothing happens. So the equation for torque is FR sine theta or RF sine theta or whatever, but torque is the cross product of force and distance. So remember, work was the dot product of force and distance. Torque is the cross product. So it's only the force that's perpendicular to the axes of rotation that is actually applying the torque. Now, the units of torque are a Newton meter. We have this thing we call a moment arm. The moment arm is the perpendicular distance from the axes of rotation to a line drawn along the direction of the force. So what the heck is that? So if we take this force here and we draw a line, and then we draw a perpendicular from the axes of rotation, that's the D. And that's right there, theta, that's dr sine theta. Now, I don't usually think about the moment arm, honestly. What I do is do a drop down from the force vector to the axes of rotation. So the axes of rotation is a line that's drawn through the pivot and the object that's rotating. And then what I do is I drop a line from the perpendicular of the force and I look, is that the sine of the angle provided? And if it is, then it's FR sine theta. If it's not, then we'll have to do a cosine, and you'll see that later. But, I should tell you what a moment arm is. Do I work with moment arms? Not really. I look at the force. Now, torque is a 3D sort of thing. If you had AP Physics 2, then you know about the right-hand rule. Well, we use the right-hand rule for torque. So what we do is you take your right hand. It's very important that it's your right hand. And you curve your hand into like a claw. I call it the claw rule when we talk about magnetism. If you curl your fingers in the direction of the rotation, it's the direction of your thumb that determines the direction of torque. So we say that a positive torque is when your thumb is pointing out of the page and a negative torque when it's pointing into the page. So if we do that, if we rotate our fingers counterclockwise, then our thumb is out of the page at us, which is a positive torque. And if we rotate our fingers clockwise, then our thumb is pointing away from us into the page, and that is negative. So it's easier to think of it in terms of clockwise and counterclockwise. So when we solve static equilibrium problems, first we have to identify all the forces. So I always draw a force diagram. So it's not quite a free body diagram, which is, a box or dot with the arrows. It's an extended force diagram. So we can show the point of application of all the forces. We get to choose the pivot for torque. That's important because that dictates where all of our distances are measured from, where all our R values are. And the pivot point you choose is totally up to you. You want to choose a point where there's the most unknown so you can eliminate them, right? Because their R value then would be 0. You identify all the forces, and then you do sum of the forces equals 0, and sum of the torques equals 0, and then you just start putting equations together. So let's take a look at 2 different types of problems that you're going to see. One is standing on a plank. So this is more of an AP Physics 1 situation. We have this person standing on the end of this plank. The plank is 10 meters long, so that means that our L value is 10 meters. We have scales here that are both a distance d from the end, and that d value is 1 meter. Here we gave you numbers so we can work with numbers. Of course, numbers make life a little easier than having to work with variables sometimes. But if we write in first, what we want to do is we want to draw the diagram of the forces. So we're going to draw the plank here. The woman here is standing at the end of the plank, so she's exerting a force of gravity. I'll give her a big mg. Sometimes in AP1 we had a massless plank. That happens. But this time we have a mass-full plank. So remember this, we're going to assume this is uniform. It looks uniform in the picture. And remember that uniform objects, the center of mass is where the force of gravity acts. So here we're going to draw a vector for the mass of the plank. We'll make that a little mg. Now, the scales, right, are exerting a normal force up. So we're going to draw a normal force up here. So that's force normal. I'll call that force normal 1. And then here, a distance 1 meter from the end, we're going to have another force, and we'll call that force normal 2. Now, if I were drawing these somewhat to scale, logically, force normal 2 should be less in magnitude than force normal 1. And I didn't do a good job of reflecting that on my force diagram. But it should be, right? Because most of if we did a center of mass of the woman and the beam, it would be somewhere over here. All right, so there must be more weight on the scale that's closer to the woman than the scale that's on the very end. All right, so if we write our equations, right, if we do a sum of the forces, these are all vertical forces, so the sum of the forces in the y equals 0. Then we have the normal force 1 plus the normal force 2 must balance or equal the weight of the woman plus the weight of the plank. So we have normal force 1, the combination of these 2 scales are going to equal the weight of the woman, which would be 100 times 9.8, right, which would be 980 newtons, plus the weight of the beam or the plank, which would be 50 times 9.8, which is like a half of 980, which would be 490 newtons. So that means that our total scale reading, when we add those scales together, we're going to get a total of 1,470, because that's our total weight of the woman plus the plank. Now, right now, we can't just solve this as it is, right? We can't write another sum of forces equation because we have 2 unknowns. So we're going to go to sum of the torques now. So if we think about the torques, right, when we do torques, we got to choose a pivot. So what pivot you choose is totally up to you. I'm just going to select this as my pivot right there. So that means that all of the distances for the woman is going to be that distance. We'll call that our woman. The distance for the normal force, again, is measured from there. So I'm going to just call that R1. And then this is going to be the distance R for the plank. So when we do a sum of the torques, right, we're going to have, so sum of the torques are equal to 0. So positive torques, right, cause counterclockwise rotation, which is what these, the weights are going to do. So we're going to have the torque from the woman plus the torque from the plank has to equal the torque from our scale 1. So we'll just call that torque 1. All right, torque, FR sine theta. All of our angles look perpendicular, so the sine of 90 is just 1. So I'm just going to, just leave that out. And so we have the force from the woman, which would be our mg from the woman, times our R woman, plus the mg, the weight of the plank, the force of the plank, times the R of the plank, has to equal the force normal from the scale times the R of the scale. All right, so normal force 1, right, we can solve for that then by dividing everything by R over 1. So now let's plug in our numbers. So normal force 1 is going to equal the weight of the woman, which is our 980, so 100 times 9.8, times the R of the woman. Well, the whole scale, right, or the whole plank, sorry, is 10 meters. This little guy is 1 meter from the end, so this must be 9 meters. So for the woman, that means her R distance is going to be 9. The weight of the plank, right, was 490, so our 50 times 9.8. The distance of the plank, center of mass, right, to here, right, the center of mass would be at 5. So our R for the plank is going to be 9 minus 5, or 4. And then we're going to divide by the distance from that normal force, right, which was here at a distance of 1 meter from 9, and that's going to be 8. So now we just got to do some algebra and do some calculations here, and we're going to get that this normal force is 1,347.5, and this is newtons, right, because it is a force. All right, so now I know what normal force 1 is. So if I go back to my equation up above here, and I rearrange and solve that, then normal force 2 is going to equal 1470, the total weight of the plank, minus my normal force 1, which is 1,347.5, and we're going to get an answer of 122.5 newtons, which is a lot different than our first scale. So our first scale obviously should be bigger. Always ask yourself, does this make sense? The first scale should be bigger because it is closer to the total center of mass of the system. So let's ratchet up the difficulty a little bit here. Let's try a problem with a ladder. I love ladder questions. I don't like to stand on ladders. So this is actually a question I ask all the time is, what is the minimum angle I can put this ladder at so it doesn't slip? Now, in this case, they gave us a static friction coefficient, 0.2, but pretty much nothing else. They did tell us that the wall is frictionless, which is interesting, but will help us from a force standpoint. But obviously, there's got to be force of friction between the floor and the ladder. Otherwise, there's no point in trying to put this ladder up in the first place. So how do we solve this? Well, we got to draw a force diagram. We got to identify all of the forces acting on the ladder. We got to set up some of the forces and some of the torques equation and see if we can cancel out everything until we get to an angle. All right, let's try that. So first thing we got to do is we got to draw our force diagram. So let's draw a picture of our ladder. We're going to say that this is a uniform ladder because they didn't tell us anything else. So the weight of the ladder is going to act at the center of mass of the ladder. The ladder is sitting here on the ground, so that's going to exert a normal force. We'll call that just Fn. It said we had static friction, and friction's opposing motion, right? So that would point towards the wall. There's our force of static friction. Of course, there's our phi right there. We have one more force here. Even though the wall is frictionless, it is sitting on the surface. The ladder is pushing against the wall, so the force of the wall is going to exert a normal force on the ladder that's perpendicular to the wall. And so we're going to draw a force here. We could call it normal force, but I'm just going to call it force of wall, just so we can keep force of wall separate from the force from the floor or the concrete slab or whatever this is sitting on. All right, so that means we have some of the forces in the x direction that have to equal 0, some of the forces in the y direction that have to equal 0, and some of the torques that have to equal 0. Let's just start with the x direction. Let's see what we got. Well, in the x direction, we have the force of static friction pointing to the right, so that's positive. That has to equal the force, the normal force provided by the wall. Now, the static friction, right, they gave us the coefficient of static friction, so obviously they want us to change the formula for static friction into Fs max, right? Fs max would give us that minimum angle without slipping. So Fs max is the coefficient of static friction times the normal force, and it's this normal force here. That's where the static friction is acting. So we're going to put Fn, and that's going to equal the force of the wall. All right. So besides putting in that 0.2, there's really not much I can do here at the x direction. So let's go to the y direction. In the y direction, in the positive direction, I have the normal force pointing straight up from the floor, or the ground, or whatever that is, and that's equal to the weight of the ladder, which of course we don't know, so we're just going to call it mg. Huh. You know what? I could replace this coefficient, so I have static friction, I could replace that normal force with mg, and that's equal to force of wall. But other than that, there's really not much more I can do with the sum of the forces. So now it's time to go to sum of the torque. So we need to pick a pivot point. And I know you're like, well, we don't know anything. So, and we want to know phi. And so you're going to think I'm crazy, but we're going to put the pivot point down here because there are two forces there and I don't know what either of them are. So how about we just put the pivot there and get rid of them? Because the length of the ladder, we can just call L, which means the force of the wall is going to be at a distance L, and the weight of the ladder is going to be at L over 2. So let's do a sum of the torques equation. So we have the torque, the wall is causing counterclockwise rotation, so the torque from the wall has to equal the torque from the weight of the ladder. All right, torque is Fr sine theta. This time I have angles. So the force of the wall, right, torque from the force of the wall is going to be the force of the wall times its distance, which is just L. And now we got to draw a perpendicular drop to the ladder here. And if we're going to do a sine, we got a phi. We need to make sure that this angle right here is phi, because that is the opposite of the force, the perpendicular drop. So that's phi. So actually, yeah, that would be phi as well. So that would be sine of phi, because we want that perpendicular drop of the force to the axis of rotation, because I don't do the moment arm thing. All right, that's equal to the torque caused by the weight of the ladder. So the force of the ladder is going to be mg. Its R value to the pivot is L over 2. Now we got to check this one. So if we draw a perpendicular drop here, right? This is the perpendicular. That would be the sine. If this was the angle phi, then it would be sine of phi. But if I look at this, in fact, if I imagine making this a bigger triangle, if this is phi, then that's 90 minus phi. That means this here is the phi. And I want to solve for phi. So instead of being the sine of 90 minus phi, that's the same thing as the cosine of phi. So that's why it's important to check your angles. It's not always the sine of the angle given. So you have to check. All right, great. So now I have an equation that I can't do anything with yet, except for maybe cancel those L's. But if I could get the force of the wall in terms of mg, or mg in terms of the force of the wall, right, then I could just cancel those. So let's do that. Force of wall, right, is equal to the coefficient times static friction times mg. So let's replace force of wall with that. Coefficient of static friction, mg L sine phi, is equal to mg L over 2 cosine phi. All right, so mgLs, those can go bye-bye. And we get coefficient of static friction times the sine of phi is equal to cosine of phi over 2. Oh, hey, sine of phi divided by the cosine of phi is then equal to 1 over 2 times the times the coefficient of static friction. So that means that the tangent of theta is equal to 1 over 0.4, right? Because the coefficient of static friction is 0.2. So that means that phi is the arctangent of 1 over 0.4. which, if we plug it into our calculator and we make sure we're in degrees, that's 68 degrees. Ha! Ha, we did it! 68 degrees, that's it, buddy. Don't do anything else. All right. Try some of those problems in your packet, and I'll see you in class.